we have been discussing the notion of orthonormality in the space R K. We looked at the notion of orthonormal sets, that is, these are sets in which any two vectors are orthogonal to each other and every vector has length 1. Then we looked at the notion of an orthonormal basis. An important outcome of this notion of orthonormal basis was that if you had an orthonormal basis phi 1, phi 2, phi k for, say, this is an orthonormal basis. Suppose this is an orthonormal basis for R k. So, whenever we had an orthonormal basis for R k, we can expand any x in R k, and that expansion was called the Fourier expansion. Expanded, this is called Fourier expansion. Expanded in terms of this basis as x equal to summation j equal to 1 to k x phi j phi j, where x comma phi j, remember, denotes the inner product. So, if you recall, the inner product x phi j is also the same as phi j transpose x. So, every vector x can be expanded in terms of the orthonormal set as a linear combination, orthonormal basis, and the coefficients are easily obtained as the inner product of the vector x with phi j. Okay. The coefficients are simply the inner product of x with phi j. This was one of the important things that we got out of this idea of orthonormal basis. Then we introduced the notion of the orthogonal complement of a set. In particular, we were interested in orthogonal complement of subspaces. So, let us say W is a subspace of R k. If W is a subspace of R k, then we look at all the vectors which are orthogonal to every vector in W. So, that set we call as W perp. W perp is the collection, it is a collection of vectors. What vectors? So, of all those vectors in R k which are orthogonal to all the vectors in W. So, orthogonality is given by the fact that the inner product is 0. So, mathematically we can write in symbols as W lambda as all those vectors, it is all those vectors in R k, this is this part, such that which are orthogonal to all the vectors. So, x comma omega must be 0, orthogonal to all the vectors. So, it should be for every omega in omega. So, W lambda is the set of all the vectors in R k which are orthogonal to all the vectors in W perp. We saw that W perp is a subspace of R k. This subspace W perp is called the orthogonal complement of W. So, every subspace has something called its orthogonal complement. Okay. We will make one simple observation. So, again we start with the subspace W of R k, and we denote by W perp the orthogonal complement of W. So, we have a subspace and its orthogonal complement. Suppose we take a basis for W. Suppose B W equal to U 1, U 2, U d is a basis for W. So, let us say dimension of W is D. So, we have a subspace of dimension D, we call the W, and W perp is the orthogonal complement of W, and we are looking at a basis for W, which will consist of D linearly independent vectors. Let that basis be U 1, U 2, U d. Now, suppose I have a vector x in W perp. This means x is orthogonal to all the vectors in W. That is the definition of W perp. W perp is the collection of all those vectors which are orthogonal to all the vectors in W. So, x is orthogonal to all the vectors in W. These basis vectors U 1, U 2, U d are all in W, and therefore, x must be orthogonal to these vectors. So, implies in particular x is orthogonal to all the vectors in the basis W, this basis B W. And therefore, what is meant by orthogonality? The inner product x comma these vectors U 1, U 2, U k. So, the inner product with U j must be equal to 0 for j equal to 1 to d. So, what this means is that if a vector is in W perp, it must be orthogonal to every one of the basis vectors. So, let us sum it up, call it conclusion 1. X belongs to W perp implies x is orthogonal to all the vectors in a basis for W, all the vectors in a basis for W. Conversely, suppose x belongs to R k is such that x is orthogonal to all vectors in the basis B W. What does that mean? This means x U j is equal to 0 for j equal to 1 to up to d. Now, take any vector W in W. Now, since B W is a basis, we can expand W in terms of this B W vectors. So, W can be expressed as a linear combination of the vectors in the basis B W, in the basis B W for W, and therefore, we have x equal to some alpha 1 U 1 plus alpha 2 U 2 plus alpha d U d. Consequently, I am sorry, W equal to W equal to this. Consequently, this implies if we now take the dot product or the inner product of x with w, I get x comma alpha 1 u 1 plus alpha 2 u 2 plus alpha k u k, but the dot product is distributive and constant come out of the dot product. This is equal to alpha 1 x comma u 1 alpha 1 x comma u 1 plus alpha 2 x comma u 2 and so on alpha d x comma u d. But now we are given, recall that we had assumed that x is orthogonal to all the basis vectors, and therefore, x comma u j is equal to 0 for every j. So, this becomes 0, which means x is orthogonal to w. So, what it says is that the moment the vector, if something is orthogonal to all the basis vectors, then it is automatically orthogonal to all the vectors. Thus, x belongs to w pur. This is true for any w. For any w we can do this, and therefore, x is orthogonal to w for every w in w. So, therefore, conclusion 2 is, if we start with the fact that x is orthogonal to all the basis vectors, then that implies x is in w pur. Comparing this conclusion, in conclusion 1 we had that if x is in w pur, it must be orthogonal to all the basis vectors, and now we have said that if it is orthogonal to all the basis vectors, it must be in w pur. So, combining conclusion 1 and 2, we get x belongs to w pur if and only if x is orthogonal to all the vectors in a basis for w. What this means is the following: we have this vector space V and we have the subspace W, and we are going to pick a vector x in R k. With the vector space V we are dealing with R k. So, we are going to pick a vector in R k and we want to check whether x belongs to W pur. So, the question we are asking is, does x belong to W pur? Now, basically in order to check that x belongs to W pur, we have to check whether x is orthogonal to every one of these vectors in this W. However, what we have now shown is, you do not have to go on checking with every vector. You choose these d samples, namely the basis vectors, and just check whether x is orthogonal to u 1, x is orthogonal to u 2 and x is orthogonal to u d. And therefore, what it says is, you do not have to go on checking whether x is orthogonal to all the vectors. It is enough if we check if x is orthogonal to all the basis vectors, then automatically you can conclude whether it is x is orthogonal to all the vectors or not. And thus, in order to check whether a vector x is in W pur or not, we have to check only whether x is orthogonal to all the vectors. Now, let us look at some examples. This idea we will use in the examples to find the W pur. Let us look at R 3 and consider the subspace of all those vectors which are of the form A, where A is now. In other words, it consists of all those vectors, every one of its components is equal to the other. Okay. So, this is along the line 1 1 1. Okay. So, now consider this space, and then it is easy to check that it is a subspace. We know how to check whether it is subspace, we have to see it is non-empty, we have to check whether it is closed under addition, whether it is closed under scalar multiplication. All these are easy things, we have done these before. So, it is easy to check that W is indeed a subspace of R K. So, let us find W perp, the orthogonal complement of W. Now, first of all, in order to check whether something is W perp or not, we have to check whether everything is orthogonal to a basis vector. So, in order to do that, we will first find a basis for W. So, clearly 1 1 1 this vector u alone forms a basis for W. Why is this so? Because this vector belongs to W and every vector in W is A times u. Okay. So, therefore, it spans W and hence it forms a basis. So, our BW, the basis for u W consists of only one vector, namely u equal to 1 1 1. Now, therefore, a vector x will belong to W perp if and only if x is orthogonal to the basis vector, and there is only one basis vector, and therefore, we want x to be orthogonal to the basis vector. Suppose x is x 1, x 2, x 3, then this says x comma u, the dot product between x and u is x 1 into 1 plus x 2 into 1 plus x 3 into 1, that must be 0. So, the only requirement for a vector to get qualified to be in W perp is that the sum of its components is 0, and therefore, the vector x is of the form alpha, beta, x 1 and x 2 can be anything, but the moment you give any values for x 1 and x 2, to make the total sum as 0, we have to make the third component as minus alpha minus beta for alpha beta in R. And therefore, we get W perp to be the collection of all vectors of the form alpha beta minus alpha minus beta, where alpha and beta belong to R. Okay. So, the original space W, which was all A now has this orthogonal component which complement which consists of vectors whose third component is the negative of the sum of the first two components. Okay. Note that V 1 equal to 1 0 minus 1 and V 2 is equal to 0 1 minus 1 is a basis for, let us call this as BW perp, is a basis for BW perp, because these two vectors are in W perp, and any vector alpha beta minus beta in W perp can be written as alpha times V 1 plus beta times V 2. Therefore, they span and they are obviously linearly independent, and therefore, they form a linearly independent set in W perp and span W perp, and therefore, they form a basis for W perp. Now, notice that W had a basis consisting of a single vector, and therefore, the dimension of W was 1, and the basis for W perp consists of two vectors, and therefore, dimension of W perp is 2, and you notice that dimension of W plus dimension of W perp is equal to 1 plus 2 is 3, which is the dimension of the original vector space in which all these subspaces live. They are all subspaces of R3. So, in this case K is 3. So, the dimension of W plus dimension of W perp turns out to be the dimension of this whole space. Okay. Note also that we have this basis for W and we had the basis for W perp, and if you put them together we get a set B which consists of these vectors U, which was 1 1 1, and V 1 which consisted 1 0 minus 1, and V 2 which was 0 1 minus 1. And this B is linearly independent and has 3 vectors, and we know that in R3 any linearly independent set having 3 vectors is a basis, and therefore, a basis for R3. So, in this example we observe a lot of things are happening, namely the dimension of W and dimension of W perp added together to give the dimension of the whole space, and the basis of W and the basis of W perp added together to give now a basis for R3. So, the union of a basis for W and a basis for W perp is a basis for RK R3. That is in this example. We will see the more general version that this is in general true a little while later. Let us now look at another example of this construction of this orthogonal complement. Let us again now consider R4, a slightly bigger dimensional space than before, and now consider the space subspace W, which consists of all those vectors of the form A, B, A plus B, A minus B, where A, B are in R. Now, once again it is easy to check that W is a subspace of R4. So, W is a subspace of R4, and therefore, we will find, let us find the orthogonal complement W perp. Now, again as before, in order to find the orthogonal complement, we first found a basis for W and then looked at all those vectors which are orthogonal to each one of these basis vectors. So, to this extent we will now go and find a basis for W. Now, from the structure it is easy now to see if I take A equal to 1 and B equal to 0, I get this vector 1 0 1 1, and if I take A equal to 0 and B equal to 1, I get this vector, and this forms a base. These vectors are in W, they are linearly independent, and any vector in W is A times U1 of the form A times U1 plus B times U2, and therefore, they are linearly independent vectors in W which span W, and therefore, they form a basis. So, this is a basis for W per W. So, what do you observe from this about dimension of W? Since there are 2 vectors in this basis, the dimension of W is indeed 2. Now, let us find W perp. X belongs to W perp. We have seen that a vector belongs to the orthogonal complement if and only if it is orthogonal to every vector in the basis for W, and therefore, X must be orthogonal to U1 and X must be orthogonal to U2. Now, suppose X is x1, x2, x3, x4. Now, we are looking in the space R4. So, x will have 4 components. Now, what does the first condition say? X must be orthogonal to u1. So, the dot product of x with u1 must be 0, u1 is this vector. So, x1 plus 0 times x2 plus 1 times x3 plus 1 times x4 is 0. So, we get x1 plus x3 plus x4 equal to 0, that is this fact. Then this fact tells us that x2 plus x3 minus x4 is equal to 0. Now, that says that there are two equations that the 4 components should satisfy, and there is going to be 2 floating variables, and so x is of the form we can choose x3 and x4 arbitrarily, then x1 has to be minus x3 minus x4 and x2 has to be x minus x3 plus x4. So, where alpha and beta can be anything, and therefore, we get W perp consists of all the vectors of the form minus alpha minus beta, minus alpha plus beta, alpha beta, where alpha and beta are real numbers. Now, clearly again taking alpha as 1 and beta is 0, we get this vector, and alpha is 0 and beta is 1, we get this vector, and that will be a basis for W perp. So, is a basis for W perp. And therefore, since the basis for W perp consists of 2 vectors, we also observe that W perp has dimension 2, and it turns out even in this case dimension of W plus dimension of W perp is 2 plus 2, which is 4, which is the dimension of the big space R 4. So, this dimension plus dimension W perp in both these examples added up to the dimension of the whole space. Again check, it is easy to check. If you put the basis of W union basis of W perp, we get these vectors u1, u2, v1, v2, where u1, u2, v1, v2 are as we observed before. Now, these are linearly independent. Check that these are linearly independent, and these are 4 vectors which are linearly independent in R 4, and therefore, a basis for R 4. So, a basis for W and a basis for W perp put together gave us a basis for R 4, and that in turn essentially gives us the fact that W the dimension of W plus dimension of W perp is indeed equal to the dimension of the whole space. Okay. Now, let us pursue this further and analyze these 2 orthogonal complements. All these analysis will be used eventually to study our questions about systems of equations, diagonalization, etc. So, now let us get back to R k, and let us say W a subspace of R k. Let the dimension of W be equal to D, and therefore, we will have an orthonormal basis. If we take any orthonormal basis for W, it will have exactly D orthonormal vectors. So, let B W be phi 1, phi 2, phi D be an orthonormal basis for W. Now, we have seen that every orthonormal set is also linearly independent, and therefore, phi 1, phi 2, phi D is a linearly independent set, and it is an orthonormal set. it is an orthonormal set sitting in the big space R k. So, here is R k and here is W. In this phi 1, phi 2, phi d are sitting. Now, since phi 1, phi 2, phi d is an orthonormal set, we have seen that any orthonormal set in R k can be extended to a orthonormal basis in R k. So, we can extend B w to an orthonormal basis for R k. Let how many vectors we will have to append? The dimension of R k is k. So, we would have to pick some vectors, how many of them? K minus d, call them psi 1, psi 2, psi k minus d, and these are going to be orthonormal, they are outside. So, let the extended basis be B. We will have all the phi 1s, that is what is meant by extension. To this we will add these, append the psi 1, psi 2, psi k minus d. So, this is now a basis for R k and it is an orthonormal basis. So, we have an orthonormal basis for, so this being an orthonormal basis for R k, we have seen that any vector can be expanded in a Fourier expansion or as a linear combination in terms of the orthonormal basis vectors, where the coefficients in the linear combinations is simply the inner product of the vector with that corresponding basis vector. So, let us sum this up. This being an orthonormal basis for R k, any x in R k can be expanded as x equal to x comma phi 1 plus etcetera x comma phi d plus x comma psi 1 plus x comma psi k minus d psi k minus d. We will write this as simply j equal to 1 to d x phi j plus j equal to 1 to k minus d x psi j psi j. Let us call this 1. Now, we are going to observe certain facts from this examination, in this expansion. Now, for this we make certain observations. Now, some observations that we will make are about these vectors psi j. Now, since this is an orthonormal basis, so every vector in this is orthogonal to any other vector, and therefore, psi 1 will be orthogonal to phi 1, psi 1 will be orthogonal to phi 2 and psi 1 is orthogonal to phi d. So, note, since B is an orthonormal basis for R k, every vector in it is orthogonal to every other vector. Right. And therefore, in particular psi 1 will be orthogonal to phi 1, phi 2, phi 3, phi j equal 0 for j equal to 1 to t. So, psi 1 is orthogonal to all the vectors in the phi 1, phi 2, phi j group, but these phi 1, phi 2, phi j form a basis for W. This means psi 1 is orthogonal to all the vectors in the basis B W for W. And just a few minutes back we saw that if a vector is orthogonal to all the vectors in a basis, then it must belong to the orthogonal complement. So, that says psi 1 belongs to W perp. Similarly, psi 2 is orthogonal to all the vectors phi j, and therefore, psi 2 belongs to W perp and so on. So, similarly, psi 2, psi 3, psi k minus d, all these belong to W perp. And therefore, we have the first observation, psi 1, psi 2, psi k minus d are all in W perp, and 2, since the whole set is orthonormal, since the whole set B is orthonormal, even this part must be orthonormal, and therefore, we get psi 1, psi 2, psi k minus d is orthonormal. So, we have an orthonormal set in W perp. We would like to know whether it is an orthonormal basis for W. Is this a basis for W perp? For this, we have to check whether every vector which is in W perp is a linear combination of this, because it is already orthonormal and hence linearly independent. Therefore, the only requirement to be checked for this to form a basis is whether it spans the space. So, for this we need to check if this set spans W perp. So, let us check that. So, let x be in W perp. If since x is in W perp, x phi j, since x is in W perp, x phi j must be equal to 0 for j equal to 1 to d. Why is this? Because some vector is in W perp if and only if it is orthogonal to all the vectors in the basis for W. Now, phi 1, phi 2, phi d forms a basis for W, and therefore, x must be orthogonal to phi 1, phi 2, phi d. And that means, the expansion for x in terms of B. Remember, we had this equation 1 which said that any vector can be expanded of this form. Now, in particular, if I have taken the x for which all the x phi j's are 0, the only thing I will get is the remaining part. So, by 1 becomes x is equal to summation j equal to 1 to k minus d x psi j psi j, which means x is a linear combination of this psi 1 psi 2. X is a linear combination of psi 1 psi 2 psi k minus d, hence psi 1 psi 2 psi k minus d span W perp. So, we have seen that they are in W perp, they are orthonormal, and now they span W perp, and hence they form a basis, an orthonormal basis for W perp. So, what it says is that if you now start with a basis for W, an orthonormal basis for W, extend it to an orthonormal basis for the whole space, the part that is coming in the extension namely in this case this will automatically be a basis for the orthogonal complement. Okay. Now, you get some simple facts from this. What do you get from this as the dimension of W perp? This is a basis for W perp. It has k minus d vectors. The dimension is precisely the number of vectors in a basis. So, dimension of W perp is k minus d, which is dimension of R k, and d was the dimension of W, which implies dimension of W plus dimension of W perp is equal to dimension of R k. So, this is a very important fact, namely that if you have any subspace W of R k, then the dimension of W and the dimension of its orthogonal complement add up to the total dimension of the whole space. This is a very useful important fact which we will use shortly. Okay. Then let us look at 1 then. The equation 1, which said that if x is in R k, then x can be expanded as sum equal to j equal to 1 to d x phi j, where this phi 1, phi 2, phi d is an orthonormal basis for W, plus j equal to 1 to k minus d x psi j, where the psi 1, psi 2, psi k minus d is an orthonormal basis for W perp. We will call this as x w plus x w perp, where x w is that first sum, x w is equal to summation j equal to 1 to d x phi j, and x w perp is summation j equal to 1 to k minus d x psi j. Now, observe that since this phi 1, phi 2, phi d are all in W, the x w is a linear combination of the phi 1, phi 2, phi d, and hence belongs to W. Similarly, psi 1, psi 2, psi k minus d are in W perp and therefore, this belongs to W perp. Any linear combination also be W. So, what this says is the vector x has been decomposed as the sum of two vectors, the first vector in W and the second vector in W perp. So, thus the conclusion is every x in R k can be written or decomposed as the sum of a vector x w belong to W and a vector x w perp belonging to W perp. Now, this shows that we can decompose it into two parts. Any vector can be decomposed into two parts, one in W and the other one in W perp. Now, are there many ways of doing this decomposition? If so, we would like to choose the correct one or the useful one, or if there is only one way of doing it, then we do not have much choice. So, is this decomposition unique? So, suppose we have two decompositions. Suppose x equal to x w plus x w perp and x is equal to x w prime plus x w prime, where x w prime are in W and x w perp and x w perp prime are in W perp. So, we have two such decompositions, say of a vector x into a W part and a W perp part. Then subtracting, we get theta k is equal to x w minus x w prime plus x w perp minus x w perp prime. Or if we take one of these terms to the other side, we get x w prime minus x w is equal to x w perp minus x w perp prime. Now, what this says is this vector and this vector are the same. Let us call this common vector as z. Then this says because z is equal to this and x w prime is in w, x w is in w, this vector belongs to w. Similarly, this is in w perp and this is in w perp, the difference of two w perp vectors is in w perp, and therefore, this is in w perp. Because w and w perp are subspaces, difference of two vectors in w will be in w, difference of two vectors in w perp will be in w. Therefore, this says z is a w vector, it is also a w perp vector, that says z belongs to w intersection w perp. Okay. Now, whenever you have w and w perp, the intersection can contain only the 0 vector, because if we now look at z comma z, treat z as a vector in w perp w and treat this z as a vector in w perp. We can do that because that belongs to both w and w perp. Now, we have an inner product of a vector in w and w perp, and that must be 0, but the inner product is the length squared, the length is 0 means z is equal to theta k, and that says x w must be equal to x w prime and x w perp must be equal to x w perp prime. So, not only we can decompose a vector x as the sum of a vector in w and a vector in w perp, but this decomposition is unique. So, what do we get? Let w be any subspace of R k, then every vector x in R k can be decomposed uniquely as the sum x is equal to x w plus x w perp, where x w belongs to w and x w perp belongs to w perp. There is a unique decomposition of every vector with respect to every subspace. This whole decomposition depends on the subspace w with which you start with. So, the moment you give me a subspace, there is a breaking up of the vector into two parts, one from w and one from w perp. Okay. The x w is called, now I can say the x w because the whole decomposition is unique. The x w is called the orthogonal projection of x onto w, and x w perp is called the orthogonal projection of x onto w perp. We see that if we know one orthogonal project, suppose we know x w, we can get x w perp as x minus x w, and alternately if we know the projection x w perp, then we can get x w as x minus x w. So, that is we have the notion of the orthogonal projection of this. So, let us look at what this says geometrically. Geometrically what this does is the generalization of the following fact that we know in 2 dimensions. Let us take 2 dimensions. Let us take this x and y axis. Suppose what is the notion of a subspace is a line passing through the origin. So, let us say this is the subspace, a line passing through the origin. Take any vector x now, draw the perpendicular from x to this. Okay. Now, this vector is what now x w is, and this vector is x w per. And what it says, we know by the resolution of forces that the force x is equal to the velocity or force, whichever vector you want to use, is the sum of these 2 vectors. And this is what is now generalized in the setup of R k. The line is replaced by a subspace W, and this orthogonal dropping is the orthogonal projection, and the difference is the projection onto the other space. So, this is the generalization of the simple projection idea which we have in geometry. Now, in geometry, when we have such a projection idea, this angle being an orthogonal 90 degrees, we know by Pythagoras theorem the length of the hypotenuse squared is equal to the sum of the lengths of the squares of the other 2 sides. So, the Pythagoras theorem says in R 2 that the length of this vector x w squared plus the length of the vector x w squared is the length of the hypotenuse square. Now, since we have generalized this projection idea, can we generalize this Pythagoras theorem also, and in fact, this is true. In fact, this Pythagoras theorem, this theorem also gets generalized. So, we have this Pythagoras theorem in the setup of R k is a general version of the Pythagoras theorem. So, W subspace of R k, W perp its orthogonal complement, x belongs to R k, x is equal to x w plus x w perp is its decomposition, where x w is the orthogonal projection of x onto w, and x w perp is the orthogonal projection of x onto w perp. This x belongs to w, x w, and x w perp belongs to w perp. Now, let us look at the length of x squared. So, then length of x squared is equal to the length of x w squared plus the length of x w perp square. This is what the Pythagoras theorem is. Let us prove that. It is a very simple proof. The length of any vector is given by the dot product of the vector with itself, but now we are given that x is x w plus x w perp. So, we write like that, and the dot product is distributive. So, we can take out the individual products. This will be x w comma dot product with x w plus x w dot producted with x w perp plus x w perp dot producted with x w plus x w perp dot producted with x w perp. The first term is the length of x w squared, because the dot product of any vector with itself is the length squared, and the second term is 0, because x w and x w perp are in orthogonal spaces, and similarly x w belongs to w and x w perp belongs to w perp. So, that is 0, and that gives me the length of x w perp squared, and hence we get the Pythagoras theorem, length of x squared is equal to is equal to length of w squared plus length of x w perp square. So, now if you look at this theorem, that any vector can be decomposed as x w plus x w perp. Now, we can add and also norm x squared is equal to norm of x w plus norm of x w perp square. Okay. So, we have so what are all the things that we have seen? You have w and you have w perp, and everything can be decomposed in terms of these two. We can decompose a vector, we can decompose the basis into two parts, one from w and one from w perp, and we can decompose the vector and its length into two parts. It is this sort of decompositions that we will be using in our analysis. We shall look at an example and see how we would use it in our matrix context in the next lecture.